So we're going to introduce how gradient descent works here as an optimization function. So you can get a pretty good idea of how it works just from considering situations that you run into in Calculus 1. So let's just draw, oh, sorry, I have to turn off this tool. Let's draw a curve and, okay, something like this. And what we're trying to do is find the location or the input that minimizes this function, which would be something like this. Okay, so we don't really know where to start looking. So imagine that we start looking at sort of an arbitrary place, like maybe we pick this place to start randomly. We go up here and we can look at the derivative of the function at this location. So the derivative of the function at this location is the slope of this tangent line, so it's going to be a negative number. So if I write the derivative sort of as a vector in one dimension, it's going to be a vector with some magnitude, and it's going to point that way. We don't usually think of one-dimensional derivatives as vectors or whatever, but we will in the higher dimensions. So let's practice doing it now. So one thing that we might do is sort of like the vector that is the derivative is pointing in the direction that will make the little point climb uphill. So what it's basically saying is that uphill is toward negative infinity. So if you want to go uphill, you need to walk a little bit that way. But we actually, that would be good if we wanted to maximize the function, but what we actually want to do is minimize it. So instead of looking at the derivative, we'll look at the negative of the derivative. So now you have a vector of the same magnitude but pointing the other direction. And now suppose we were to adjust our guess by sort of adding this vector to it. It would put us somewhere over right here. And now we could do this again. So again, the derivative of the curve at this location is negative, so it's sort of a vector pointing this way. But because we want to minimize the function, we make that the negative of what it was, and then we add that vector to where we were. And what it's done is it's made us walk down here. So notice something interesting when we get to this point. Now the curve is less steep than it was. So that means that the derivative at this point is going to be a less negative number, which means that the magnitude of this derivative vector is going to be less than what it was before. And we make it negative again. So what this causes us to do is to take a step in this direction, but now it's kind of a tiny step. We take kind of a tiny step. And we end up here, and now let's play the same game here. Okay, so now the derivative here is a slight positive number, so it wants to go sort of like that, but we make it negative because we want to minimize. And that makes us take a tiny little step back the way we came. And you can see what's happening here is we're kind of converging toward the input that minimizes the curve. So some bad things could have happened when we were doing this that just happened not to happen. So this is the basic idea for gradient descent, and so this is kind of a simplified idea, even a simplified presentation, even in low dimensions, because suppose that there's like a local minimum or something. So if you start doing gradient descent on this, you know that the global minimum actually occurs for this input. But if you start looking for the global minimum right here, then what's going to happen when you follow the gradient descent algorithm is you're going to sort of roll down to the bottom of this bucket, and you'll get stuck here, and you'll never find the global optimum. So that can happen. That's a real thing to worry about. But with logistic regression and with linear regression, the things that we are trying to minimize are convex. So they only have one global optimum, And so we don't need to worry about that for linear regression and logistic regression. It does come up when you're minimizing really complicated things like neural networks, but not for what we're doing right now. Okay, so hopefully everybody understood that. Let me tell you about one other bad thing that might happen here that we have to consider. Let me open up another page. So suppose that we are doing this gradient descent process, and so here's the curve, and we're trying to find the minimum, which happens right about here. So suppose that we guess that this is where the minimum is, and we take the derivative and we get this big positive number. So of course we reverse the sign, and so that makes us move this way. Suppose that this thing is so steep right here that it makes us jump all the way over here. So that's possible. If I drew it steep enough, then it would make us leap all the way over here. And if this were sort of a symmetric situation, then when I did the same thing over here, now I would just leap back to where I was. And what would happen is that I would sort of thrash back and forth between these things, and my point would never sort of roll down to the bottom of the bowl. So there's a factor that you use in gradient descent to prevent that from happening, and it's called the learning rate. So it's like a small quantity, like 0.1 is what we're going to use most of the time. So instead of using that whole vector here, let's start over with the learning rate. So, again, we explore this point, we get this big positive number that makes us want to take a big negative step this way. But instead of going all that way, we're only going to go 10% of that. So our rule is going to be, instead of following the vector with its full magnitude, we're going to cut the magnitude of the vector that we follow and to 1/10 of what it would have been. So instead of going this whole way, we only go 1/10 of that way. And then we keep doing this, so then we would end up like here. So it takes more steps, but there's less chance of thrashing. Sometimes gradient descent you can get into situations where it doesn't converge well, and you have to worry about adjusting the learning rate. But most of the time, especially for logistic regression and linear regression, just using 0.1 works fine. Okay, so that's pretty much it, and we can even write kind of an algorithm for the whole thing right now if we wanted to. But let's before we do that, let's look at the two-dimensional version. So I'm going to open this thing that I made on CoCalc for studying gradient descent. Let me see where stuff is. Is there like some little hand or something? Okay, all right, great. So I just made a contour plot. So you can see that the function that we're working with right here is this thing. So this is z equals x squared plus y squared plus xy. If you want to see what it looks like, you can plot it just by typing. If you type this into the Google search bar, then you'll get a three-dimensional graph of the surface, and you can kind of see what it looks like. So now this, instead of having a derivative, now we really do have a gradient. So what is the gradient of this function f xy? So it's a vector itself. The first element of the vector is the derivative of this with respect to x, which happens to be 2x plus y, and then down here we get 2y plus x. Right. So this is itself a function of two variables, x and y, And kind of similar to the way the derivative works, if you take a point here, this is a contour plot, what its derivative wants to do is send you in the direction of maximum increase. So if you think of the gradient as a vector, which it is, it's going to point sort of uphill. But because we're minimizing things, we don't want it to point uphill, we want it to point downhill. So we make it negative. And we also have this, even in 2 dimensions and higher dimensions, we still have this thrashing issue that I talked about earlier, where it might jump like this back and forth. So we don't want that to happen, so we also use the learning rate that I talked about earlier. So let's try to, so here I'm playing around with this a little bit. I implemented the gradient of this function in Python, so it just returns, it's a and b instead of x and y, but you can recognize this as the derivative. So eta is what the book calls the learning rate, so that's what we're going to call it too. This p is just an initial guess of where the minimum might be. You can see from this graph that for this function the minimum is actually at 0, 0. But in this code we're gonna make 4, 4 our initial guess. In practice, you want to use you can use a random number. For logistic and linear regression, you could use the 0 vector as your initial guess, but in other situations, the 0, 0, 0 is kind of weird, and it might put you like at the bottom of a local minimum or something like that. So just so you start at a generic point, you can start at like just use a standard normal standard Gaussian distribution. So in Python that would be np.random randin, and then whatever the shape of this should be, like in this case it should be 1 row and 2 columns, whatever. All right. So this path variable is I'm just keeping track of all the points that I've been to before. That's because I want to plot like a little Hansel and Gretel trail that the guess follows. So we get the gradient of the initial point, and then the next point is the previous point minus eta times the gradient. And so this is the update rule. So p equals, let's use the notation that we actually do use. So the next w is going to be equal to the previous w minus eta times the gradient of j with the previous w pulled in. So this is the equation, or the update rule, that really is gradient descent. Let's just keep following this code here and see what happens. Let's go over to the next page. So I do this a few more times. So I get the gradient of q, and then r is the next thing, and then I get the gradient of r, and s is the next thing, and I stack all these things up and I look at them. So if you're following along at home and you want to implement this code yourself, a fun thing to do is to take the learning rate away. So remove eta and see what happens, and you will actually see thrashing in this example. So this wouldn't work without eta. And now let's look at a picture of what's happening. So this is p, and then I forgot the order that they came in. P, Q, R, S, or something like that. So you can see that they're looking for the bottom of the bowl, and they're moving there. So it's steeper here, so this was a larger leap initially, and now it's kind of slowing down because the magnitude of the gradient is less there because it's more flat. And here's a lazy gradient descent algorithm that only works this. So you will have to implement this yourself, but when you do, don't come look at this sorry excuse for a function, because it only works for these toy examples. one big difference between what we're doing right here and what we actually do in machine learning is that our gradient actually depends on this big set of training data. So it's the J that we use is much more complex than this F thing, because it involves n data points. So you have all these x's here that are also influencing the thing, and so that's not captured at all by what's happening there. Here's some other examples. So I just started at a different place. Now I added a color bar so you can kind of see how many iterations it's taking to converge. So if you start down here, then it takes about 10 iterations to converge. And this is going to be a little bit boring. I just do this several times in a row. So now it's start over here, and it converges in about 10 steps. So let's keep going and see the next thing. Alright, so something kind of interesting happens here, which is instead of converging in 10 steps, now it converges in about 30 steps. And it still doesn't even look too good to me at 30. And so you can ask, why did it take so much longer? And it has to do with the way this dimension is kind of exaggerated. So you can see this thing is pretty far from being circular. It's kind of elliptical, and this dimension is exaggerated compared to this dimension. And so what happens is the thing has to walk a long way. The thing has to walk a long way in this dimension, and so that can make convergence take a longer time to achieve. So that is like incredibly exaggerated in real data sets, because we've been looking at some data sets. Suppose that you have your big matrix X, and it has different columns. So one of the features that determines a column in this thing might be like age and years, which is going to be a number between 0 and 120. And another column might be income in dollars, let's say. So income in dollars is going to be a number that's between negative whatever. But a typical range would be from 0 to, most people make less than 250,000. So this is, but the scale of this column is orders of magnitude different. So if this is what is this? It's like 10 to the 5th, and this one is like 10 to the 2nd. And what that does in terms of this picture, you can think of it as making these incredibly stretched out ovals, and it messes up gradient descent, because it doesn't make equal steps in equal dimensions. It has to make little steps in small dimensions, and it has to make huge steps in bigger dimensions, and it just ends up not working well. I tried to capture that a little bit here by making, you can see that the Y scale now goes from minus 1,000 up to positive 1,000, and meanwhile the X scale just goes from 0 to 200. So you can see that it does kind of a crazy thing. So it starts, remember, it's supposed to be climbing downhill, but it starts kind of going uphill, and then it realizes that it's doing something wrong. And this is kind of, I guess this is like a numerical hiccup or something, but also notice that the scale of the axes sort of exaggerate the extent to which it actually veers off like this, because it only went over by like 150 units in the X direction, but while it's doing this, it's gone up by 750 units in the Y direction. So if the aspect ratio was 1, it wouldn't look like that. It would look more like this, just a little bit of a curve to it. So I'm going to stop here and then pick up again in a different video.